Hi all, welcome to another video of subject DC machines and transformers based on KTU syllabus, and we are on module 4. So today we are going to discuss a problem from the transformer. Okay, so here we are covering three different problems in three different sets of problems in a single problem. Okay, that is we will find the equivalent circuit referred to the OC. Okay, based on the open circuit and short circuit test, and we will calculate the regulation of the transformer, and we will calculate the efficiency and maximum efficiency. Okay, so it's very important. You can expect a part of this problem in the university question paper. So this is the question. A 15 kVA 2300 bar 230 volt 58 single phase transformer gave the following test data. Open circuit test. If you are doing the open circuit test, the voltages are V0 is equal to 2300 volt, I0 is equal to 0.21 ampere, and W0 is equal to 50 watt. Short circuit test, Vs is equal to 47 volt, Is equal to 6 ampere, and Ws is equal to 160 watt. Find the equivalent circuit referred to high voltage side. This is the first question. And second one, calculate the full load voltage regulation at 0.8 power factor lagging when the load voltage is held at 220 volt. Then third point, you have to find what is the efficiency at half the rated load at unity power factor. And last one, find the maximum efficiency and corresponding output power. Okay, so it's a very important problem. Normally the questions like maximum efficiency and the corresponding load at maximum efficiency, normally it's asked in the question paper. So how we can do that? So we know that in an open circuit test, the wattmeter reading will be give the corresponding iron loss. Okay, iron loss, that is core loss, Pi. So Pi, it is constant for whatever may be the load, the Pi, the iron loss will be a constant, so it is 50 watt. Okay, and here the from the short circuit test, the wattmeter reading will be the copper loss. Okay, that is copper loss corresponding to this 6 ampere. Okay, copper loss corresponding to the 6 ampere. Okay, and first we have to find the equivalent circuit parameters referred to high voltage side. High voltage side is here, it is primary, so we have to find the equivalent circuit parameters referred to primary. Okay, so from the open circuit test, what we obtain is actually we have to calculate the value of R0, X0, then magnetizing current Im, and working amount of and energy amount of current IE. Okay, that these four can be find out from the open circuit test, and from the short circuit test we can find the corresponding equivalent resistance and reactances based on a particular side, that is based on the primary and secondary, that is R01. Okay, R01, X01, and R02, X02 can be find out using this short circuit test. Okay, so we can move to the answer. So first we have to find the equivalent circuit parameters. So here the given parameters are current, power, and voltage. From the open circuit test we obtain these three values, and we know that the no load power factor cos phi 0. Okay, cos phi 0 is equal to P0 by V1 I0. That is, we know that power P is equal to V I cos phi. Okay, P is equal to Vi cos phi. So we are considering the case of a no load case. So phi cos phi 0 is equal to P0 by V1 I0, and by substituting the values we will obtain the power factor as 0.1035. Okay, and using this cos phi 0 we can find the energy component IE. I is equal to I0 cos phi 0. I0 is already there in our question. I0, that is 0.21 ampere, and cos phi 0 we have already found here. So just substitute that values and we will get the energy component IE. And for finding the magnetizing amount Im, either we can use the equation of Im is equal to I0 sin phi 0, or we can use this equation, that is, we know that the no load current I0 will be the vector sum of IE and Im. So Im can be found using the equation root of I0 square minus IE square. Okay, whatever may be the method, we can use that. either of these two methods we can use. Okay, I0 is 0.21 and I is 0.022. Okay, so we can find the magnetizing current from here. So the magnetizing current IM. Okay, so this parts we will obtain, this part of the equivalent circuit we will obtain from this no load test. Okay, so this is R0, this is X0, and IE flowing through this R0 and IM is flowing through this X0, and here is our I0. I0 is actually divided into IM and IE. Okay, and next we can take the short circuit test. Here also the R0 and X0. R0 and X0 can be find from the values of this voltage. Okay, that is, it is 2300 volt. So R0 is V1 by IE. IE and IM already we have found here. So V1 by IE, we will get R0, and X0 is equal to V1 by IM. Okay. In all question based on the open circuit test, we are using the same equation. Okay, V1 is the corresponding voltage. Okay, voltmeter reading during the open circuit test, and IE and IM we are finding. Okay, and if you are taking the case of short circuit, here the short circuit current is 6 ampere and the corresponding voltage is 47 volt, and the power input on short circuit is 160 watt. That is the copper loss corresponding to this 6 ampere. Okay, so first we have to determine on which side we are doing this open circuit test. Actually, the open circuit normally the short circuit test. Normally the short circuit tests are done on that is the low voltage side is short circuited. Actually, while we are doing the short circuit test, we will short circuit the low voltage side, and we will connect our equipments on the high voltage side. Okay, so we will short circuit the low voltage side and we will connect the equipments, that is pump, watt meter, current, voltmeter and ammeter on the high voltage side. Okay, so here as per the values given here, the high voltage side is on the primary. Okay, it's on the primary. So initially from the short circuit test we will obtain the resistance and reactance values on the primary side, that is R01, X01 and like that. Okay, and later we can convert that R01 and X01 to R02 and X02. Okay, if this rating was given as 230 bar 2300, okay, if it is given like this, then we know that the high voltage side is on the secondary. So normally the low voltage side is short circuited and equipments are connected on the high voltage side. So the equipments are connected on the secondary here in this case. So initially we will obtain the values of R02 and X02. Okay, and later we will convert that into R01 and X01. So here the high voltage side is on the primary, so we will obtain the values on primary, that is Z0 and R0 we will first find. Okay, so Z0 is equal to corresponding voltage by current, that is the short circuit voltage by short circuit current, that is impedance we will obtain, and the corresponding R01. Okay, that is the resistance, and resistance referred to primary. R01 is equal to copper loss, PS by I square, because we know that copper loss is equal to I square R loss, P is equal to I square R, so R01 is equal to P by I square. Okay, so Z0 and R01 obtained, and X01 can be found using the equation root of Z01 square minus R01 square, and we will obtain the X01 also. Okay, so these are the parameters of equivalent circuit, and we will write the equivalent circuit parameters here, R01 X01, R0 X0, and we can also write the currents here. Okay, so that's the first part. We can expect that this question for a 5 mark or a 6 mark. Okay, up to this X01. Okay, and sometimes the question may include the regulation, asked to find the regulation and efficiency. Okay, so that's the second part of this question, that is calculate the full load voltage regulation at 0.8 power factor lagging when the load voltage is held at 220 volt. Okay, and we know that actually the equation for regulation, okay, equation for regulation is I2 R02 cos phi plus I2 X02 sin phi. I2 is taken common outside divided by E2. This is the equation for voltage regulation. Okay, so here in the question itself the power factor is given as it is mentioned that as it is 0.8 power factor lagging. Okay, 0.8 lagging. So here the we are using the plus sign. If it is leading, we have to use a negative sign here. Okay, I2 R0 to cos phi minus I2 X0 to sin phi. Okay, so here normally in all the cases the power factor may be given as lagging. Okay, so we will use the positive sign here, plus sign here. So for that we have to find, we already found R0 to X0 to, and we know the value of cos phi, and we have to find this I2 and E2. Okay, I2 and E2. So actually we can find the I2. I2 is the rated current on the secondary side. Okay, so here as per our question, it is a 15 kVA transformer, and rated voltage output. Okay, rated voltage output is 230 volt. So the current at the output is 15 kVA by 230 volt. Okay, so here the current I2 secondary current is 15,000. 15 kVA means 15,000 VA. Okay, 15,000 by 230, it is we will obtain it as 65.22 ampere I2. And load voltage is 220 volt. Okay, in the second question it is given that load voltage is held at 220 volt. Okay, 220 volt. Otherwise we may take if it is not saying 220 volt, we can also take it as 230 volt. Okay, but normally it will specify the value of voltage there. Okay, the load voltage is held at 220 volt. So here the V2 is 220 volt, and we can find the E2, that is no load voltage induced EMF on the secondary E2. So E2, we know that in the case of a transformer, this is the primary side and this is the secondary side, just for a rough work. Okay, and in the secondary side there may be resistance and reactance, and E2 is here and V2 is here. So E2 can be obtained by V2 plus the losses in these components. Okay, so we can write E2 as E2 is equal to V2 plus the losses in this component can be written as I2 R0 to cos phi plus I2 X0 to sin phi. Okay, so this is actually the losses, I2 R0 to cos phi plus I2 X0 to sin phi. I2 is taken common. Okay, so E2 will obtain it as 224.84 volt. Okay, and we can use that in the full load voltage regulation equation. Okay, so the full load voltage regulation equation can be written in two methods, that is I2 R0 to cos phi plus I2 X0 to sin phi. Okay, by E2, this is one equation, and also actually this one is actually the loss in a transformer. So actually it is obtained by E2 minus V2. Okay, we know that E2 minus V2. So regulation can also be written as E2 minus V2 by E2. Okay, so here we have already found all that values. E2 we have found, V2 we know, and I2 R0 to cos phi X0 to, all that we have already found. Okay, so we can use either of these two equations for finding the full load voltage regulation. Okay, so in the question itself they have used E2 minus V2 by E2. That is E2 is here, V2 is here. So E2 minus V2 by E2. Okay, we will obtain it as 2.152 percentage. That is the voltage regulation. Or we can use this equation also, because all I2 R0 to cos phi, all that we know, just substitute that values, and also we can use this equation for finding the voltage regulation. Okay, so that's the second case. And the third case is what is the efficiency at half the rated load at unity power factor. Okay, we have to find the efficiency at half the rated load. Okay, half the rated load means the current is half and also the load. Okay, load is taken half. Okay, so here we can find the third one. So the efficiency, we know that the equation for efficiency is output by output plus losses. So here output by output plus losses are iron loss and copper loss. Pi is the iron loss and x square Pc is the copper loss. Okay, so here the Pc is actually the full load copper loss. Full load copper loss is actually the Pc, and x here is the load ratio. Okay, so and we have to find the corresponding output corresponding to the half the rated load. In the question, so they are asked to find the efficiency at half the rated load. Okay, so we have to find the output at half the rated load. So the output at half the rated load and at one power factor. Okay, unity power factor is, you know that the rated kVA, it is 15. It is given as 15. Okay, so half the rated load means 15 by 2. Actually it is 7.5. Okay, 7.5. And normally the output we are written as the watt while we are finding the efficiency. So we have to multiply that kVA with our power factor. So here in the third part it is given that we have to take the power factor as 1 unity power factor. So just multiply that power factor with this value, that is 15 by 2 into 1. So we will get as 7.5 kilowatt or 7500 watt. Okay, so this is the output on half the rated load. Okay, if you are asked to find out efficiency at 3 by 4th of the load, okay, 3 by 4th of the rated load, we have to multiply that rated kVA by 3 by 4 and unity power factor 1. Okay, and also if you are asked to find the efficiency at half the rated load and at 0.8 power factor, we have to multiply that rated kVA by 1 by 2, and instead of this power factor 1 we have to use 0.8. Okay, so here in the question itself we are asked to find the efficiency at 1 unity power factor. That's why we are using this one here. Okay, and this is the output. And the iron loss, we know that it is constant through whatever may be the load, it will be constant. So PI is taken as 50 watt. Okay, it is actually obtained from the open circuit test. Okay, and the full load copper loss, we can find the full load copper loss. That is here the PC is full load copper loss. Okay, so the full load copper loss can be find, you know that the copper loss, okay, copper loss is I square R. Okay, copper loss is I square R. So here in the question itself we have the copper loss at 6 ampere. Okay, that is 160 watt at 6 ampere. So here, but we have to find the full load copper loss, that is when the current is rated current. Okay, we have to find the full load copper loss. So full load copper loss PC, okay, we know the equation for PC is equal to I1 square R corresponding. Okay, so we can write a ratio that is we know that the copper loss at copper loss at 6 ampere is 160 watt as per the short circuit test. So we can write a ratio there, PC by PS. PS is the short circuit value. Okay, short circuit test copper loss obtained from the short circuit test, and it is equal to IS square R. So here R cancelled. So PC by PS equal to I1 square by IA square. Okay, so PC can be written as I1 square by IA square into PS. Okay, so that is actually written here. Okay, PC is equal to I1 square by I1 by IS whole square into PS. And also here we are taking the primary current I1. Okay, why? Because the short circuit test, okay, we are taking the copper loss we obtain from the short circuit test. Normally we know that the short circuit test, the low voltage side is short circuited there, and we will connect our equipments on the high voltage side. So here, as per our question, the high voltage side is on primary. Okay, so we have to primary means we have to calculate the, we have to use the current and the primary. Okay, that's why we are taking the current value I1 here. So I1 is the corresponding kVA rating. kVA rating of the transformer is 15 kVA divided by corresponding voltage on the primary, that is rated voltage on the primary is 2300. So 15,000 by 2300 we obtain the value of I1. Okay, and IS is 6. IS is 6 already we obtained from the question itself, short circuit test values. IS is 6, WS is, that is PS is 160. Okay, PS is 160. So we will obtain the full load copper loss as 189 watt. Okay, 189 watt. So PC full load copper loss PC is 189 watt, and here we have to find X square PC. Okay, X square PC. So here the X means the corresponding load. So we are finding the efficiency at half the rated load. So X means 1 by 2, half. Okay, so X square PC is 1 by 2 square into 189. So the copper loss at half the rated load is 47.2 0.25 watt. Okay, so don't make a mistake, that is, this is the full load copper loss, and if you are asked to find the copper loss at half load, don't take the exact half of this 189. Okay, because the copper loss is depending upon the square of the corresponding load. Okay, so here 1 by 2 is the corresponding load, so half square into 189 will obtain it as 47.25. And after that, substitute the values here. Output we obtain, it is 7500, and PA is 50 watt, and PC corresponding to half the rated load is 47.25. Okay, so substitute that values and we will obtain the efficiency as 98.72%. Okay, so that is the third case. And also, if you are asked to find the efficiency at 3 by 4th of the load, at that case we have to multiply by 3 by 4 square here. Okay, if the load is 3 by 4th, x square PC means 3 by 4 whole square into PC. Okay, and the last one is we have to find the maximum efficiency and the output power corresponding to the maximum efficiency. Okay, so this is the fourth one. Sometimes the questions in the question itself, they are asked to find the load at which the maximum efficiency occurs. Okay, instead of these values, they are also asked to find the load at which the maximum efficiency occurs. Okay, so that's actually calculating here. Okay, so first we know that the maximum efficiency condition is when the copper loss is equal to core loss, that is the variable loss is equal to constant loss. Okay, that is the condition for maximum efficiency. So here the maximum efficiency occurs at when the iron loss Pi, okay, Pi is equal to our copper loss. Okay, so here the corresponding in the question itself, if they have asked to find the load at which maximum efficiency occurs, so we have to find the x first. Okay, x, so the value of x will be root of Pi by PC. Condition, if you are considering the condition of maximum efficiency, the load at which maximum efficiency occurs, the equation will be equal to x is equal to root Pi by PC. Okay, so Pi we know, and the corresponding PC we know. Okay, full load copper loss we know, so we will obtain the value of x. Okay, and after that we have to find the kVA corresponding to maximum efficiency. So the kVA corresponding to the maximum efficiency is x into rated kVA, so root of Pi by PC into rated kVA will obtain the 7.715 kVA. And the power output corresponding to maximum efficiency. Okay, power output corresponding to maximum efficiency, we have to calculate that kVA with we have to multiply that kVA by the unity power factor. Okay, so here in the question the condition for if you are finding the maximum efficiency, it is not mentioned the actual power factors here. Okay, so we can assume the power factor as 1. Okay, so in the second case they have mentioned the power factor 0.8 power factor, and the third case they have mentioned the power factor as 1, and in the fourth case they have not mentioned the power factor, so normally we will take the value as 1. Okay, so normally the power factor is taken as 1. So the power output corresponding to maximum efficiency. Okay, power output corresponding to maximum efficiency is the corresponding kVA at the maximum efficiency, that is 7.715 kVA into 1. 1 is the power factor, so we will get it as 7.715 kW, that is 7715 watt. Okay, and we know that for finding the condition for maximum efficiency, output by output plus losses. So here the losses means maximum efficiency occurs at when iron loss is equal to copper loss. Okay, so here the iron loss, when iron loss is equal to copper loss. Okay, so iron loss is 50 watt. Okay, so we can write as 2 Pi. Okay, iron loss plus copper loss. Okay, output by, we know that output by output plus Pi plus PC. Okay, that is iron loss plus copper loss. So these two will be equal at the case of maximum efficiency. So we will take the value of Pi. We know that Pi is constant, what will be the load, so Pi is 50 watt. So we can take Pi instead of this x square PC or PC, we can write also the value of Pi there. So Pi plus Pi 2 Pi. Okay, so condition for maximum efficiency, always it will be the equation, that is output corresponding to maximum efficiency by output plus 2 Pi. Okay, just remember that equation. output by output plus 2 pi, because pi and pc are constant there. Okay, so pi we know 50 watt, and we have found the corresponding power output corresponding to maximum efficiency, and we will obtain the maximum efficiency is 98.72%. Okay, so here in this, say in a single question we have covered almost three questions. Okay, three different essay question. Okay, so I hope all of you understand the question well. So thank you.